I would now like to introduce and invite Gilbert Camoin, who is, of course, the head of ECORD, but a very experienced and long-standing member of the scientific ocean drilling community. And he's going to talk about the Tahiti Sea Level rise drilling expedition 310.
The title of my talk here is called Reef Records of Sea Level and Climatic Changes During the Last Deglaciation Window into the Future. It's just linking the a topic of societal relevance to what we have done in the past with the ODP and with IODP. In fact, I will talk about Tahiti Sea Level Expedition 310, of course, but I will also talk about the Great Barrier Reef Environmental Changes Expedition, because these are two sisters expedition. Before I start, I just want to thank the conveners to invite me to present this, but also to organize this MSP focused workshop. I think it's this is really a great initiative, and this will serve definitely the ECORD community, but for me, the IODP program as a whole. We'll also introduce here a couple of my major collaborators on this topic, and you see the names here. There are two British here, Gideon Anderson and Alex Thomas. So the current and the future changes in the Earth system pose some of the most pressing scientific and societal issues at the moment, especially how will climate, the ocean and ice sheets will respond to warming from greenhouse gas forcing. These are the two sea level records we have since more than a century now. On the left side here, the sea level record by tide gauges since the beginning of the 20th century, and the satellite altimetry since, let's say, almost 3 decades, let's say. What we can see here is that despite the fact that, of course, the satellite altimetry is more accurate to measure the sea level changes here, is also that we went from something like a 1.7 millimeter year sea level rise to 3.2 millimeter per year sea level rise during the last 3 decades. And the sea level is constantly rising there. So concerning the mechanisms we are talking about here, we are talking about ocean thermal expansion, but more here about ice sheet and glacier melting. What is important is also to try to predict what the sea level change will be in the future. These are two scenarios here. One which is called here optimistic scenario, saying that by the end of this century, we could have a sea level rise of something like between 5 and 6 millimeters per year. And a more pessimistic one where we are talking about more than 10 millimeters per year sea level rise. So just keep in mind these two figures, because this will be, again, a part of the discussion later on. So the objectives for us as geologists or paleoclimatologists are to evaluate the rates and magnitude of future sea level change, and also to try to forecast the impact on coastal areas. And this is, of course, a large social impact, because at the moment, 700 million of people are living in this low elevation coastal zone, which is less than 10 meters above sea level. There will be something like 1 billion in 2050. And this is for sure here, the water levels may rise very rapidly. To better predict the future, we need to obtain past sea level records associated to climatic warming episodes on timescales which are comparable to the current or the future climatic changes. What we know from the current ice sheets is that they are melting. Their melting is really increasing very rapidly over the last 2 decades, let's say, here in Greenland, here in Antarctica. And the fact is that there are at the moment very poor constraints on the timing, the rates, and the relative contributions of the various ice sheets and glaciers. The frightening stuff here is that really we are talking about something like the equivalent of 65 meter of equivalent sea level concerning the contribution to the global ocean. Talking about the past sea level records or the past climatic records, we think immediately, of course, of the Quaternary, and this is a reconstruction of the changes in sea level over the last 800,000 years, as it was reconstructed from many ocean drilling cruises based on isotopes in forams, for instance. And this shows that there were intervals of something like 100,000 years, and with some, of course, some additional shorter cycles of a few tens of thousands of years. The magnitude of these sea level changes is about 120 to 140 meters. And of course, these changes from glacial stages to interglacial stages are involving, of course, sea level change, but also the ice volume and temperature changes. When we are talking about the sea level indicators, we have just talked about the forams in the ocean, and especially the isotopic records. The tropical coral reef records are able really to provide a kind of unparalleled records of the timing and the magnitude of these quaternary sea level changes. This is, as I used to say, by dating the fossil sunshine. The fact is that the corals are accurate sea level indicators. They are living at certain depth in the ocean. They are linked to the light in the ocean. So that means they are able to track really the fossil sunshine. The other thing also for record of sea level change and an indicator is also the ability to be dated. Concerning the corals, they are giving an accurate chronology based on the uranium-thorium series for the last 600,000 years, and C14 for the last 50,000 years. If we are now plotting the coral reef records of sea level change in the Quaternary, you will see clearly that, of course, when you are going back in time towards the left here, there are less and less records. And you will also, I will also mention here that most of these red spots here showing the coral ages are concerning areas which are located in very active tectonic areas, which are not probably the best areas in the world to reconstruct accurately sea level change. Two periods here are of major interest. So the last interglacial, which is the youngest similar warm period, something like 125,000 years before present. And the other one is the last deglaciation, which is from the last ice age, something like 25,000 years to the present, when we had dramatic climatic changes and sea level changes, mostly related to the collapse, the major collapse of the large ice sheets. And what happened here is that you are going from low stands to high stands through very rapid sea level fluctuations and abrupt climatic and environmental changes. And these rapid changes have dominated the Quaternary throughout. So the objectives here for us is to understand the timing and magnitude of sea level change. This is also includes, of course, the reconstruction of ice volumes, but also to better understand the mechanisms of sea level change, to relate them to major climatic phenomena. We are also concerned here by the impact on coastal systems and including, of course, the reef response to the sea level and environmental changes at various timescales. The problem you have seen in my previous slide is that most of these quaternary reef and sediment archives are mostly stored on modern coral reef slopes. And the fact is that to get access to them, these are two beautiful images. One is here Barbados, and you see these wonderful reef terraces, which are now between, let's say, the sea level and something like 100 or 200 meters deep, and the same here around Papua New Guinea. The problem here is that to get access to this, there are different means. I mean, dredging, sampling with submersibles, but of course, these are not totally reliable in terms of the water depth at which you are able to collect your records. But of course, you have to use reef drilling, and this has been done only a few times in the recent past, as you will see, and IODP went to that very recently. So before 2005, there were basically only 3 records tackling a little bit the last glacial sea level rise. The most complete one was, of course, Barbados, covering the whole period. But the problem with many uncertainties concerning the sea level indicators that they were dealing with. So that means that this sea level record was not considered as fully reliable. And then there were 2 other records, one on Papua New Guinea, which is an uplifting area. So that means probably not the best, again, the best area to get an accurate sea level record. And Tahiti already, when we drilled some land, we carried out some land drilling here on the modern reef, and we were able to go back to 13.8 kilo years before present. But these few records already provided some information here. We were dealing for the last glacial with a magnitude of sea level change of 120 to 130 meters, duration of about 20,000 years, with an average rate of sea level rise, but something like 10 millimeters per year. The major and very important information here was also the occurrence of these very rapid sea level rise, one which was around 14,000 years BP, and the other one something like around 11,000 BP. These are what we call the meltwater pulse MWP, meltwater pulse, which are related to major collapse of the major ice sheets. So the objectives here to understand better the sea level change during the Quaternary are to locate the maximum low stand during the last glacial maximum. So when really here during the ice age. So that means that this gives you, a way to figure out how much ice was on the Earth, and also to better reconstruct the occurrence, the timing and amplitude of these catastrophic periods here called the meltwater pulses. Also for the reef geologists, which is important here, is that these periods of very rapid sea level rise were interpreted as giving what we called reef drowning events. That means that something that just interrupt the reef growth for some time, and giving maybe sometimes a kind of succession of different generations in the reef system. And we are then very interested in reconstructing the nature of the environmental changes, the reef geometry and the architecture, and the reef development and accretion rates. What happened since 2005 was that with a single proposal that we submitted in 1999, when the MSP concept was not existing yet, but it was more or less, at the same time then when the first Arctic proposal was submitted, we proposed to drill modern reefs with the IODP operations. And the objectives here were to reconstruct the timing, the course of this last glacial sea level rise, the nature of the environmental changes, but also the reef responses to sea level and environmental changes. And we proposed two major areas, two major regions. The first one was Tahiti, because we knew from the land drilling that the reef record was probably very promising here, and we then proposed to drill all around the Tahiti Islands, but also to drill on a continental margin along the Great Barrier Reef. And this is what we obtained. The two records are very complementary, and this is the reason why I will present today a kind of very rapid reconstruction of what we found concerning the sea level rise, and very briefly about the reef responses. Of course, I will not talk about the other things like the nature of the environmental changes, because we will need probably another hour to talk about the temperature and salinity changes here. These are the two expeditions that we implemented in 2005 and 2010. Tahiti was the first IODP drilling in modern reef environments, and definitely, I mean, these two expeditions were correspond to the most extensive geological research on coral reefs. These are just some numbers to give you some insights on what we have done on the expeditions. And just one number here I would like to stress on as the recovery. You heard from Dave McEnroy the other day that we were dealing with something like 58 or 60% recovery in Tahiti, but of course this is the standard recovery calculation that we have in IODP. But the problem in reefs is that you are dealing something like 30 to 40% porosity, I mean cavities. So concerning the hard material, the carbonates, we recovered 92%. The recovery was a bit lower in the case of the Great Barrier Reef, 60%, but 92%, this is exactly what you need when you want to work on high resolution. This is just a very quick overview of what we have done in Tahiti with drilling 37 holes. In blue here, this is the last deglacial reef sequence. And in the other color here, I've indicated the older Pleistocene reef sequence, and we were able to get very good records in all the isotopic stages, but of course, I won't have time to talk about this today. So a total of more than 600 meters of cores. And again, the average porosity is between 30 and 35%. When we are talking about porosity, we are talking about big cavities in reefs. So then I come to the sea level reconstruction. You need two things. First thing, the accurate chronology. In case of Tahiti, the internal precision for geochemistry here is perfect for the uranium geochemistry. The mineralogy is perfect. Less than 1% calcite means that the corals are as fresh as modern ones. And for this, what we have done was to work on paired U series and C14 dates on these pristine corals. So the precision that we could get on, for example, on the 15,000-old coral was between 30 and 50 years, which is for a geologist, I mean, something like a dream, right? To work on such a high resolution. I will not talk about the calibration of the C14, which is a long-lasting initiative among the geochemical the community, but we have done that in Tahiti, and we were able to add a little bit more of some points concerning calibration. The second important item here is to work on with accurate sea level indicators. These are the corals that we were able to recover in the Tahiti cores, and you see that by comparison to the modern ones that you see here below, that we also investigated, we were able to reconstruct the paleo water depth. So that means the depth at which these corals were living at the time of these reefs were alive. In addition to the corals, we didn't restrict to the corals. We worked also with other organisms living with corals like algae and encrusting foraminifers. So these are just a few. We'll go very quickly through this last glacial, and we start with the last glacial maximum. So that means during the ice age, when here between 28 and almost 22,000 years BP, the sea level position was between around 113 meters below modern sea level. And you see that the sea level is rising very, very slowly, with accretion rates of the reefs here less than 2.5 millimeters per year, which is pretty slow. So this period was followed by a very sharp drop in sea level. You see here about 20 meters sea level drop, meaning that at the time, I mean, the ice sheets were building again. That means that it was a very unstable period, and a rate in sea level drop between 15 and 20 meters, 20 millimeters per year. Then when we arrive around the 20.5 kilo years BP, then we start with the last deglacial processes until 16 K in the Great Barrier Reef here. And we have a sea level rise of about 15 meters during this period, with an average rate of 3.5 millimeters per year. So it's not very rapid. It's more or less the same rate that we face at the moment. In the modern environments, we have something like 3 point something millimeters per year. The accretion rates here were of something like between 2 and 4 millimeters per year. And you see that the sea level was, the reef was not growing as quickly as we could have thought during this period. But what really happens is that the major changes happens sometimes after 16,000, and especially during what we call the meltwater pulses. And the first one that we were able to document very precisely in Tahiti starts at 14.65 kilo years BP, and these meltwater pearls lasts for something like 350 years. So what is important here is that first we were able to give a precise timing of these meltwater pearls, and previously it was supposed to be much younger than it is really. And I will come back to this in a second. What is important also is to note that the rate of sea level rise during these pearls was something like 40 to 45 millimeters per year. And to provide these 16 meters in amplitude means that in 350 years means that you had to melt something like 1.5 to 3 equivalent of the modern Greenland ice sheet. So it was a very, very catastrophic period for the climatic system on the Earth. The fact that these pearls is now the precise timing is given here, the fact is that it's coeval to major climatic changes called here the Bolling Halo Road. I mean, this is a very famous climatic event, and the fact that the meltwater pulse is linked to this one means that really we are dealing with major collapse of large ice sheets. We have also reinterpreted the Barbados record that were published some years before Tahiti, and we were able to redefine, in fact, the meltwater pulse in Barbados, and it seems that we are dealing with something which is similar to Tahiti and coeval with Tahiti. So again, the meltwater pulse 1A is coeval with this boiling inception, which is a major climatic event. And then through the modeling of all these data, Bob Kopp we worked with us and defined that the fact that Tahiti and Barbados are very similar, I mean, their records are very similar, means that the modeling shows that there was a large Antarctic source for the meltwater pulse 1A. And funny enough was that a few years ago, the expedition 382 with the JOIDES resolution demonstrated exactly the same thing. The large Antarctic source for the meltwater pulse 1A was demonstrated by very large fluxes of these iceberg rafted debris here. And the peak flux of this Antarctic ice sheet discharge was exactly of the same age and duration than the meltwater pulse 1A from Tahiti. So then there's another direct evidence for an Antarctic contribution for this meltwater pulse 1A, this major thing. Without going in details, it was just to show you the beauty of the cores that we had in Tahiti. And because we were able in some sites, 9 sites in fact, but this is one example, one site where you can really recover the meltwater pulse and record the meltwater pulse in the cores. So this is the start of the meltwater pulse here, roughly, with these robust branching cores, which look like this in modern environments. And then suddenly you will see that you lose them after a while to end up with something which is this kind of cores, these very thin called branching poraitis. Those ones are growing very quickly. I mean, the growth rates are much higher than the ones from the previous calls. So that means that the reef starts to adapt more or less to the very rapid sea level rise. And then at the end, you end up with something which is a deeper water core, this called the encrusting Montipora. They are deeper. That means that the reef more or less lost the game until against the sea level rise. Another very interesting data here is that concerning the second pulse here recorded in the Barbados, we don't record anything in Tahiti. There's no significant discontinuity during this period, and the sea level is just rising all the way through. There's no reef drowning recorded on Tahiti and the GBR at the time of what we supposed to have around 11,000. So this changes a lot what we could think of the dynamics of the ice sheets during that time. And based on the reconstruction of the uplift of Barbados, some American colleagues thought that that was probably a bias related to the tectonic setting. I mean, this is probably not existing, at least with such an amplitude here. And to finish the story here, with the land drilling, both in the GBR, Great Barrier Reef, and in Tahiti, again, we don't find any evidence of discontinuity around 11,000 years for the meltwater pulse 1B. We are dealing with very fast growing reefs and an average rate of sea level rise between 6 and 10 millimeters per year. For instance, here in Tahiti, 10,000 years old is about 40 meters deep. That means a sea level rise of 10 millimeters per year. And this was drilled on the modern reef of Tahiti on land. Without going in details here, just to say that in both cases, we're talking of land to sea transects, even if on land we didn't drill with ICDP, but at least we have done transects all the way through. And with the sedimentological data and the reef geometry data that I didn't have time today to present, then we reconstruct the evolution of reef through time, and especially what we call here the backstepping means that the reef had to go towards the island to just with the, let's say, the influence of sea level rise, because it couldn't catch up, it couldn't keep up with the sea level rise, so he had to move back towards the island. It's exactly what we have seen here on the Great Barrier Reef. The only way in that case to catch this story is to go through a land to sea transit. And to summarize very quickly, the Tahiti Great Barrier Reef sea level curve, which is here presented, is probably the most accurate record of the last deglacial sea level rise, and that means that it has impacts on the calculation of the ice volumes and to reconstruct also the dynamics of the ice sheets. We documented the reef responses to rapid sea level change, and we had good insights on the environmental changes during the last deglacial sea level rise. I didn't present this, but I mean, there are many colleagues who worked on calls of different ages to reconstruct the changes in temperatures, in sea surface salinities, etc. And we were able to connect this sea level curve to the last 6,000 years here when we worked on the French Polynesia and outcrops here for the last 6,000 years, giving us a little bit more of the history here. And then if we want to put some numbers here, you see that for the last deglaciation, we are talking about 11 millimeters per year on average. You see that there are some periods during which we had a very rapid sea level rise during the meltwater pulse 1A, something like 45 millimeters per year. But again, I mean, the average is 11 millimeters per year. If you go now and compare to what we had during the last interglacial, but more important here, what we have for the recent and the future. For the last 2 decades, we are talking about 3.2 millimeters per year. So this is something which is similar to what we have seen during the early deglaciation, or what we see over the last 6,000 years. But now if we are going to the 21st century and the various predictions I gave at the very beginning of this talk, we are talking about 5.5 to 12 millimeters per year. 12 millimeters per year is already more than the average for the last deglaciation. And depending on the future here, we could get some episodes which are maybe similar to the meltwater pulse that we experienced around 14 point something thousand years ago. And these are the maximum and average refraction rates. That means that with such rapid sea level change, the reef systems, but also the coastal systems, will be in danger for the future. And my last message will be for the young generation. So if you sail on an IODP expedition, first, it's unforgettable. Secondly, you will get friends and you will have collaborators for the rest of your life, like Jody Webster here, or Dave McEnroy, who was staff scientist on the IODP Tahiti expedition and was now the ESO operator. And with that, thank you for your attention. Thanks a lot for listening to me.
Thank you very much, Gilbert. It was a really fantastic talk. Nice to see all those sunny places as well. It's surprising how many people either like to be really cold in the ice or in the tropics. Yeah. Any questions from the audience? I can see some applause coming from the emojis. Any questions? While people think of questions, I mean, what's next? What's in the mix for future reef drilling or sea level rise drilling? You know, what are the next things to do, or has it all been sort of sorted out?
This is a pretty good question. I mean, at the moment in the system, we have two proposals, two reef grading proposals. One is about more or less the same period I was talking about on another area in the Pacific, on the Sabine Bank, which is offshore New Caledonia, okay, Southern Pacific. And the other one is a proposal that could become an expedition maybe before the end of this program or the start of the next one, which is on Hawaii. And this one is led by Jody Webster, the last photo I showed from Australia. The idea here is that because Hawaii is subsiding very rapidly, that means that all these reef systems were bathed only with marine waters. So that means that they are perfectly preserved, they are pristine, and they target to drill different terraces around Hawaii just to make sure that they can reconstruct on the long term, longer than what I've done with Tahiti and the Great Barrier Reef. So this is, for me, important not only for sea level change, but also to get nice corals to reconstruct the sea surface temperatures and sea surface salinities, pH, etc. So that means reconstructing all the climatic parameters during this long period. So these are the two proposals we have in the system at the moment. But I would say if I would be able to submit another proposal, I will go definitely to other periods, other transitions, and especially the isotopic stages 3 and 4. That means that something which is between 100 and between 40,000 years BP.
Yeah, I mean, yeah, one of the big topics of scientific interest in the UK and around the world, of course, but is the stability of ice sheets and the potential for very rapid deglaciation and very rapid sea level changes, as you've highlighted here, of what was it, 45
Correct.
millimeters a year.
Correct.
Do you have any thoughts about how you would, is there a record of what was happening, say, around Antarctica, that would tell you why that was happening, or the mechanisms that happened by?
That's at the moment, I mean, already what I wanted to highlight in my talk was to also to show the correlation between what we had in the tropics and what Mark Webber especially got in during the IODP Expedition 382. Just to show that, and you remember that we both wrote the current science plan, and there was a beautiful diagram showing a transect from the tropics to the ice sheets. It's exactly what you are saying at the moment. So what we need is to get more records. And then, I mean, concerning the mechanisms, we will probably deal more with the modeling. Okay, so with the records, we will get, I mean, some insights on the timing and amplitude and everything, but then we have to go to climate modeling to better understand the mechanisms for this. Yep. But again, I mean, the link with the deep water was shown already in my talk, and this is quite amazing to see this transect throughout the globe, in fact.
Okay, let's see. Are there any other questions? Are there any hands raised up? Okay, well, thank you very much, Gilbert and Jason, for a couple of really fabulous talks. Oh, one thing I was going to remind, I remember seeing some borehole optical images of your Tahiti holes that showed all the cavities, and that was a tool that was specific to be able to be used on a mission-specific platform. We've actually used similar tools in Oman. But actually, that's a new, another option that you have with mission-specific platforms that's not available for the JR or for the Chiku. So there are circumstances, and there were workshop proposals before where people were talking about looking at permeability and fractured permeabilities, where those sorts of tools could be very, very, very useful. They
Yeah,
give much cleaner pictures than the sort of the blurry images of formation microscanners and such like.
I totally agree. I mean, in our case, I mean, we were dealing with, I mean, a resolution of about 1 or 2 millimeters. I mean, that means that really, I mean, when you get the images of the borehole itself, I mean, you have the impression that you are just in the field looking at a cross section, looking at an outcrop. It's just fabulous. I totally agree with you. That's another opportunity provided by the MSPs. Yes.
Okay, well, thank you very much, Gilbert. Thank you.
You're welcome.
Jason, thanks for joining our workshop here.